All right, we can get started. Welcome back. I know you all missed me, and likewise, as always. Where we left off on Wednesday is we were looking at the components of the performance equation and what that means in terms of aspects of that that are directly something we can impact as computer architects versus aspects of that equation that are impacted by other parts of the hardware and software layers of abstraction in computing systems, right? Some things we can modify based on the algorithm that we've chosen, things like the instruction count. Other things are directly, maybe more closely connected to underlying VLSI and semiconductor implementation, things like what resulting clock frequency we can get. But then the architecture sits kind of in the middle of that, as we've seen, and there's many aspects of that, like how many cycles per instruction do we have on average, is something that our design decisions can directly impact. And where we left off on Wednesday was just this somewhat vague question of, looking at our CPI and performance equation, and the whole idea is how can we reason about our underlying system just given that equation and some potentially artificial numbers associated with it. I like vague questions. I like vague questions because they make you think and make you have to kind of describe what you know and maybe think about what you don't know yet and why you can't answer certain things. This one's quite vague, so it's probably not a good quiz type question because there's a whole host of answers that are perfectly valid for it. So where we had left off on Wednesday was my way of attacking this type of question, this class of question, which is oftentimes an instruction mix would be given in terms of frequency. 30% of the time we're doing this type of instruction, 40% of the time we're doing this type of instruction, and it's all very artificial. And that's fine. We have our CPI equals one processor we're building currently in the labs, but real world chips have a variety of CPIs depending on what the instructions are doing and how we've implemented them. The way I like to answer these questions is to, instead of worrying about percentages, which I think can become a little too high concept in terms of trying to figure out what the percentages really correspond to, I just say, let's assume there's just 100 instructions that are executing for a given task. It doesn't change the math. At least to me, it makes the math a little bit just easier to get my mind around, which is if we assume 100 instructions, then those percentages that were on the previous slide can then directly correspond to instruction counts instead. So it was 50% of our instructions were ALU instructions. Instead, that if we assume there were 100 instructions total, that just means there's 50 ALU instructions. And so instead of trying to calculate as the textbook would lead you towards a CPI times a frequency count to get this zero point 0.5 CPI times frequency value for the type of analysis I like to do for these. Instead, it's, we have 100 instructions total. We know the CPI is 1, that's a given. So 50 cycles are spent on those ALU instructions. And you can do the same. The math works out to be the same. The answer you get works out to be the same. I just think it's much easier to calculate your average CPI based on calculating actual number of cycles and then calculating actual number of instructions and then just dividing the two. So the somewhat vague hypothetical is, what is the impact of having that MIPS displacement based memory addressing mode? First off, what is the impact is not really well defined, but the assumption that allows us to kind of work our way through the question. So if we assume that for a given workload, 50% of the loads and stores have a zero displacement, the assumption is the other 50% don't, right? So if we didn't have the displacement-based memory addressing mode, which is not a term we've been using a lot, if I wanted to phrase this more in the terminology we've been using, it would ask something like, how many cycles are we saving by having load and word instructions that allow us to do an add operation as part of the load and word instruction? That's probably based on what you've been doing in Lab 4 and whatnot, that's probably the more precise way to phrase that. How many cycles do we save by having the load and word have that constant embedded in them that allows us to give us base address with a constant offset? That's the displacement. And if the assumption is 50% of our loads and stores for a given workload have a zero displacement, again, the corollary to that is 50% do have a non-zero displacement and actually need that value. They need the 4, right, or the -4, or whatever constant we have next to the base address we have in our memory there. So if 50% do require that, well, then we can pretty quickly reason about what the impact would be of having that by just looking at if we assumed we originally would have had 100 instructions, 30 of those instructions would be loads and stores, right? That's just working out the percentages. And okay, 30% or 30 instructions of our 100 total instructions. And consequently, 50% of those would have a non-zero displacement that we could now not support in the load and word instruction itself. We would need an additional ALU instruction to do that math, which is always valid, right? As we've programmed our loads and stores, I've always said, well, you could do it either way. You could always do an add immediate instruction and then always have a zero displacement, or you have that built-in constant. So let's use that if we can. But if we didn't have that built-in constant, for those 30 instructions, 15 of them would then essentially require an additional instruction to do that additional add immediate math associated with it. And our CPI would change. Certainly the number of instructions we'd have to support would change. We'd have to have an additional 15% more instructions for the same task. And that's, given the question itself is vague when it asks what is the impact, there would be a negative impact on performance. You could go further into that question. I mean, that's why it's potentially a good question. You could definitely go deeper into it and say, well, perhaps, although it's certainly not a given, if we no longer had displacement as part of the load and the store instruction, perhaps the CPI for loads and stores would no longer be equal to 2. Maybe that would be equal to 1 in this new processor design. The question doesn't say at all, right? So it's entirely left open for interpretation what would be happening in terms of the cycles associated with those instructions. But we could at least say, based on our knowledge of the ISA, if we couldn't do those adds as part of the loads and stores, we would need additional add instructions. As opposed to just vaguely answering that, we at least have some numbers we can back it up and say, well, specifically, we'd have 15% more instructions on average to support those non-zero displacements. That's all the questions. You wouldn't have necessarily less cycles because it depends, right? We would still have, that's why it is a little vague. You would still have all the same loads and stores. They don't go away. They're still there. So you're starting with the same baseline of 150 cycles. That's still there. And then we'd be adding another, 15 cycles to support those 15 additional add instructions for it. So the CPI would change, and certainly our performance would get worse. So our overall runtime would be worse if that's the case, assuming we're not getting a significant change to the CPI or clock frequency. I mean, that's the kind of answer you could give. Well, by getting rid of this add part of the critical path for our load word, our critical path would get reduced, and we'd be able to increase the clock frequency. Those are all valid paths to take for this question. The only numbers we really would have to work with would be what's given in terms of the instruction count here. Yeah, and Tyler, your thought process for that is perfectly fine. It's sufficiently vague. There's no wrong answer if you're going down that path. The question like this would be asking about can you reason about the relationship between those quantities of clock frequency, CPI, instruction count, and resulting performance. That's all you can really do with a question like this. And finally, and I think we covered this in enough detail, there are other submetrics that one tends to see. One that was very common for a period of time, and I think we have to be a little careful with this, would be millions of instructions per second. So that is exceptionally painful. This MIPS, that's awful, right? This MIPS is instructions per second, or millions of instructions per second. That is really unfortunate in the context of this course as a potential metric. How many instructions can my processor execute as a potential performance metric? It's not MIPS the ISA. So billions of instructions per second maybe is an easier, we'll call it BIPS instead, so we don't have to conflate the two acronyms here. But that had historically been a very common way to market a processor of, well, look how many instructions this processor can execute. But I think we now know, we don't know it in depth for an actual implementation, But even just given those plots of certain instructions have a certain cycle count, other instructions have a different cycle count, and the instructions are doing different things, we, I think, know now that just counting the number of instructions that are executing is not necessarily a meaningful performance metric. It depends what those instructions are doing. Sometimes we do want to have fewer instructions per second if those instructions are doing uh, something important. So this example is a very synthetic one as well. Ultimately, and I think this is the primary takeaway again, as we talked about on Wednesday, the key performance metric we care about is runtime, is measured in seconds. So for this question here, it talks about two different compilers getting tested. So the ISA is the same. We assume the clock frequency is then the same. And really the only then the two components of our performance equation we have control over would be the instruction count and the average CPI for those instructions for our application. So if we imagine that we have three different categories of instructions, the Class A, Class B, and Class C instructions that each have a varying number of clock cycles associated with them, we could look at what the output of the two compilers provide. And I know you can't necessarily read that whole thing there, where the first compiler has 5 million Class A, 1 million Class B, and 1 million Class C instructions. I think we can do the math in our head. That's 5 million cycles plus 2 more million cycles plus 3 million cycles total for 10 million cycles. Running at 1 gigahertz, that's 10 to the 6 times 10 to the negative 9. So 1 microsecond is how, 1 millisecond is how long that code would take to execute on that compiler on that processor. Whereas the second compiler is generating 10 million Class A, 1 million Class B, and 1 million Class C. That's 15 million cycles. So that'd be taking 1.5 milliseconds to execute. So ultimately, we already would know, all else being equal, 10 million cycles versus 15 million cycles at the same clock frequency, well, that's 1 millisecond versus 1.5 millisecond. Compiler A, or the first compiler, is going to be emitting better code. And that's ultimately what we care about. But if instead we fell down this trap of looking at how many billions of instructions per second can my processor handle, or in this case, the resulting code is demonstrating, then in this case, the second compiler would look to be a better option for us. Because while it is an extra 50% more cycles here, the average CPI for that code for the second compiler is going to be better because it's a larger percentage of those Class A 1 cycle instructions. And so according to MIPS, again, when it says down there, according to MIPS, that's according to our instruction throughput of how many instructions per second are we executing. We would have, I believe, the mistaken resolution that the second compiler is giving us a better outcome. But ultimately, performance and all we ultimately care about is measured in time. It is possible that the creators of MIPS, although it's not the same people who created that concept, hated students. I love students though, so it balances out in the end. And this is something we did mention a couple of times, but I don't think I was that explicit about it, that when we talk about speed up, this is the same of any type of relative quantity we wanted to measure. Right? We're back to physics problems again, but in terms of speed up, unless a question or unless an assumption is phrasing it in a completely different way, when we're trying to understand the speed up between two different compiler optimizations or two different architectures or two different anything that's measured in time, that speed up is just that relative performance difference. And that's just something that, don't overthink that. Don't subtract the two. There's other ways you can take a ratio and things like that, but in terms of relative speed up, this is generally what we're interested in, that what is the old runtime, and it's not necessarily old versus new. What is design decision A's runtime divided by what is design decision B's runtime? And that would give you the relative speed up of B over A. So the example given there is correct, that if our original or option A takes 2 seconds and the new option B takes 1.5 seconds, our speed up is going to be that 2 over 1.5. And so that makes sense in that if we have positive speed ups of greater than 1, that only is the case when our new runtime is less than our old runtime. And so the larger the ratio, the more the speed up. And you can also refer to speed ups of being less than 1 And that's accurate. It's just you have to be very careful with your terminology to say it's technically a slowdown at that point. But when we refer to speed up, we're just referring to that relative ratio between the two. I wanted to get to Friday Fun Day stuff today, but there's a couple of things that I still think are big picture concepts here. This is a pretty important one, and let's take our time with it. So you may have already read about this. Those of you who've been doing the associated reading in your textbook, this is definitely a an important lesson for life. But beyond that, it's a good way of analyzing computer architecture and speed up. So this is Amdahl's law. Um, I always used to say that compared to the original early visionaries in either physics or electrical engineering who have long since died. Our computer engineering visionaries are still alive and with us today, but then that's not the case. They've all died in the last few years. So Gene Amdahl is this nice grandfatherly looking person who was a senior engineer at IBM and then really became an entrepreneur in the computer architecture space. You may not have heard of him. He was very much a contemporary of Seymour Cray, for example. So if you've heard of Cray, very similar companies, just different levels of success, both considered early pioneers in the computer architecture space. This is a relatively straightforward observation. You can think of it as a law of diminishing returns. Before we worry about the math, which does look kind of annoying there, let's not overthink what he is referring to when he made this original observation. Um, it has to do with where we spend our time in optimizing anything, but certainly as it refers to computing performance, this is a valid way to think about it. We can always break down the runtime of anything into two components. This is just a definitional thing. This isn't some technical observation necessarily. That if we have, let's say this is a plot showing the runtime of something. So this is time as it is advancing from, in this case, left to right here. This could be an application that's taking a certain amount of time on your processor. This could also just refer to entirely software optimization as well. This is not limited to looking at architectural optimizations, but it's useful for that purpose as well. That's the runtime. It could be measured in seconds, but let's measure it in terms of percentage of runtime. This is 100% of our application's runtime. And we are interested as good engineers in doing some optimization to it. If you don't want to think of it in terms of microarchitectural optimizations, which I understand, think of it in terms of you have this code base that you're running on your laptop and you'd like to make it go faster. Okay? It's not fast enough for your needs. You're not getting enough frame rate or whatnot. You'd like to make it go faster. We can always then split up this runtime into two regions, two arbitrary regions, but two regions, where there's going to be a certain percentage, and that's going to be referred to as F in terms of the actual formalization of this. That is the F that we are attempting to make faster. We are trying to optimize this percentage. And optimize is a terrible word for a lot of reasons. I'll just say it, we're trying to make faster. That's what we mean by optimize, right? We've been using that term. It doesn't refer to optimality or anything like that in our context. That's a certain percentage we are trying to make go faster. And the parameter that he uses in his formalization is alpha. So we're trying to make this whole region go alpha amount faster. Yes, we'd like to fastimize that portion. Thank you. You're on a roll today. And then accordingly, if F percentage is the amount that we're interested in making go faster to fastimize, there is the remainder, which is just 1 minus F percent. Because it adds up to 100%. Or the whole, or the 1, right? That is the rest. This is the amount we want to make go faster. This is the rest, which we are leaving alone, at least for now. And that's always going to be the case. However you look at a software optimization task you have in front of you, that there's always going to be some subset you're targeting trying to make faster, at least in any given point in time. And there's always going to be some portion that you are not going to be looking at, not trying to make faster, at least in that point in time. there's a common heuristic that you tend to see across many such industries. In computing, the equivalent rule is also referred to as a, I see it referred to as 85-15 and things like that for Pareto, but 90-10 rule is a very common one you see as a rule of thumb, that 90% of our runtime in general, so 90% of that bar is spent in roughly 10% of that code. And that's referring to either lines of code, static instruction count, um, and you may come back and say, well, no, that's not the case. I definitely had code where it was equally distributed. That can be the case. We can design a piece of software that has any such property. That's just a general, heuristic observation that in general, across many, many such code bases, a large percentage, and we'll say 90 just to throw a number on it, a large percentage of your runtime is spent in a relatively small, block of your code in terms of lines of code. And that makes sense if you think of loops, right? I mean, oftentimes you'll have a lot of very flat sequential code, and then you'll have this deeply nested for loop that's doing your actual work. It's doing your image processing. It's your main game update engine. It's the main task that is actually getting updated. That's a very relatively small amount of code beyond just all the other boilerplate, initialization, shutdown code you may have, but it's going to correspond to a very large percentage of your overall runtime. So this isn't just a theoretical thing we're potentially interested in. It's also potentially a feasible thing that we are interested in F% of our code in terms of our runtime. F can still be relatively large. We can potentially attack 90% of our runtime in only analyzing 10% of our code and only trying to make 10% of our code faster. And again, if we go back to the speedup equation, right? So Amdahl's law is just applying that speedup equation. There's nothing more to it than that. And the limits then of that speedup equation. Where and this was from the previous slide, our speedup is the ratio of those runtimes, right? It's what did our processor or our program take in terms of time to execute before we had tried to fastimize the code, and what does it take now? I'm going to accidentally use that term in a proper technical conversation, and I'm going to get made fun of, and that's okay. And we have the runtime associated with what it was previously. That is the T old, right? That is the T old. And in terms of what that's going to be, okay, so we still have T old here, and we can make T new faster, right? But T new is still going to be a function of T old, right? And it's going to be based on how much can we speed up. That F that we're interested in, and you can call that F speed up, I just referred to it as F here, divided by how much we made it faster, our alpha. That was 90% of the code, and we're making it 9 times faster. Well, then what was 90% of our runtime now can maybe drop to an equivalent of a 10%. But then there's still the rest, right? There's still the rest of the code that we're not making any faster. And that's our 1 minus F. And yeah, 1 minus F, and since I added another parenthesis there, which I don't really need to, there's our parenthesis there. So T old is what the original runtime was. We have what our new runtime can be, and it's just a function of the amount we can speed up, but as well as the amount we couldn't speed up before. If we don't want to think of it in terms of percentages, which again, percentages can be a little abstract for our purposes, think of it in terms of seconds. The code originally took 100 seconds, right? That's the other way we can reason about it. And we decided we're going to really optimize 90 seconds of those 100 seconds by some factor. So our new runtime is going to be a function of that 90 seconds of which we're making a certain factor faster, but we still always have that 10 seconds. We still always have whatever that remainder is going to be. And consequently, we could just cancel out the T old. So the actual original runtime isn't really relevant for the Amdahl's law observation, that our total speedup is going to be limited by that, right? F over alpha plus 1 minus F. And that's all it's really showing here. I use A versus alpha. I may not have known how to do alpha in PowerPoint when I put this together a while back. Maybe this is all obvious to you in some sense, that there's a percent you speed up, there's a percent you can't speed up. But there's a fundamental limit, and this could be thought of as a law of diminishing returns or an observation of diminishing returns here. And that limit really tells us a couple things. Well, certainly we should focus on that 90%. If you're trying to make your code faster, the 10% is pretty irrelevant, at least to start. So making that common case fast, make the code for which your F is really large faster, and at least for now, ignore the rest. But the second part is equally important, that you're going to be always limited by the 1 minus F. If you're only speeding up the F, then the limiting factor is whatever is in that 1 minus F. And if you start to throw some real numbers on it, and let's take a minute here. So I'd like you to think about this question. I know this concept just came up. I got it. It's not something you've been studying for months. But just for software optimization problem, if we suppose that we have a program that runs in 100 seconds on a machine with a multiplication responsible for 80 seconds of this time. Question asks, how much do we have to improve the speed of that multiplication, be it instruction, be it functional unit, doesn't matter, it doesn't say this core block called multiplication. How much do we have to improve the speed of that multiplication if we want the program to run 4 times faster? I'd like you to take a minute and try to plug that in. We haven't been doing breakout sessions, and I don't want to deal with it now because people may be mid-nap right now. But take a minute on your own, individually. There you go, Nicholas. Just take the remainder of the minute. That answer probably only makes sense if you've got it. So we'll walk through it together briefly. As always, I'm very dependent on the two faces that I can see. Looks thoughtful, contemplative, not bored yet. Give me the bored sign, and I will circle back here. Okay, not bored at all, of course. Okay, so there was a question in the chat which I think is valid, but I would say, again, we've just introduced this topic, but I would say is not ambiguous for this particular question, where if the goal is to make something 4 times faster, faster would be referring to speed up. So in that case, don't twist yourself into a pretzel. If you get a question that's asking about speed up in this term and is giving you percentages of runtime, it's going to be an Amdahl's law question. So I think the question is always straightforward once you recognize that, okay, this is a law of diminishing returns type question. This is an Amdahl's law question. And then once you recognize it, it's straightforward. If you don't recognize it as an Amdahl's law question and try to think about CPI and how can I change the CPI, you're going to get really wrapped into a pretzel. But in terms of an Amdahl's law question, yes, and speed up is that ratio of T old versus T new. The nice thing about the question is because of how the math works out, where we can actually ultimately cancel out the actual runtime values, we don't actually care what the old runtime is and the new runtime, although we can plug in numbers if that will help you. We just care about what that speed up would need to be. So in terms of this question, we're given what we need to know. So we are told that for the speed up is equal to 4. And we're also told, in this case, multiplication, and I don't want to get this wrong, I have to tab back to the question. The multiplication is responsible for 80 seconds of a 100-second runtime. So in this case, the best way to reason about this question would be just to say F equals 0.8. It's an Amdahl's law question, so then it's asking for what is alpha. So that at that point, it just becomes arithmetic, which we can do here. What are the odds I get it correctly on the first try? But we'll try. So we just plug it back into this equation. So 4 then equals 1 over zero point 0.8 over alpha plus 0.2. 0 0.8 is f. 1 minus f is then 0.2. We can then, if we really want to, we can multiply. Well, let's all watch me struggle with fourth grade math. We can multiply both sides if we want to kind of get that denominator out of there. We can get 3.2 over alpha plus 0.8 equals 1. 3.2 over alpha equals 0.2. Alpha then equals 16. Whew. Okay, I was actually quite worried there for a minute. Yes, thank you. I appreciate that. Okay, you'll be allowed to use a calculator if this was an exam, but yes, that's how you would reason about that type of question, and it's all synthetic. We got it. But I think the takeaway is kind of interesting personally. Maybe it's because the numbers just don't seem as easy to accomplish as you would think. Perhaps, at least to me, that's part of my takeaway. That okay, so the answer for this first question is 16. But maybe intuitively, and maybe it's just me. It just seems like, well, that's a lot of alpha. That's a lot of speed up required. That by making multiplication 16 times faster, which right is an incredible amount faster, I think. Right, making something 16 times faster is not a trivial thing. In doing so, even though multiplication is by far the most important component of this application, 80%. That's a big chunk of my time. I've only made the overall speed up 4 times faster. Alpha wouldn't have units in this case, so alpha would be relative performance improvement. It'd be a ratio of old runtime to new runtime of that multiplication component. So if it took 64 seconds before, well, it took 80 seconds, right? So that would be the other way to do the math. We have the actual numbers here, right? Multiplication took 80 seconds previously. Now it's going to take 5 seconds, right? That would be that 16 times speed up. Consequently, our performance originally took 100 seconds. Now it's going to take 25 seconds because we still have that 1 minus f component, right? We still have those 20 seconds hanging around that we didn't touch at all. And that's going to be our limiting factor here, right? But to me, I still think it's a little counterintuitive and maybe a good way that if you want to get that 4x speed up, your boss comes to you and says, well, I need this code to be 4 times faster. The answer is, well, you should do the Amdahl's law first, right? Before you try to attack this problem, because 4 times seems maybe reasonable. But to do so, you have to take this common component and make it 16 times faster. And then let's say you do a tremendous job. You're of course, you got great Iowa State training. You're able to make the multiplication 16 times faster. Those University of Illinois kids weren't able to handle it. The Minnesota guys have no idea. You've made it 16 times faster. Your code base is now 4 times faster. Boss comes by next week and says, yeah, 4 times actually wasn't good enough. We actually need it to be 5 times faster. We can plug that back in to this equation here, right? If it's 5 with the same 0.8, well, what winds up happening? I have to move this over based on where my screen's getting blocked on my side here. If it's the same exact question except it's 5, maybe you can do this in your head now because 5 would correspond to 20 seconds, right? But let's just run through the Amdahl's law math, right? Where now it's 5 equals 1 over 0.8 over alpha plus 0.2. I gotta move that over. And if we do the math there, now we're left with 4 over alpha equals 0. So alpha equals, this is going to look a little awkward, right? But alpha would then equal infinity in that case, right? And that kind of makes sense. If we go back to the real world seconds numbers, that you now have to go back to your boss and say, well, 4 times I was able to work some late nights and get working. But to make it 5 times faster, the multiplication is only 80 seconds of our original runtime. To make the overall runtime 5 times faster, our total runtime would now need to be 20 seconds. And we're not even touching 20 seconds of our total runtime. That 20 seconds, again, corresponds to this kind of partially shaded region here, right? So to make our overall runtime 20 seconds, our multiplications runtime has to now correspond to 0. That would require effectively an infinite speed up here. And at that point, you can say it's probably not likely. But again, that's an interesting thing, I think, that it's just the way the math works. There's no real cleverness to it. But ultimately, you're very limited by that 1 minus f proportion of your runtime. And it's not possible in this case, under the assumptions given, to make it 5 times faster. At least that would be the takeaway. And certainly 6 times faster certainly wouldn't be possible if you could somehow make it 5 times faster. Because even 80%, which seems like a decent amount, limits you to 5x faster. And even numbers that seem really great, like, I'm going to optimize 99% of the code. And I'm just going to completely delete it entirely because I realized 99% of my runtime wasn't needed. You're still limited by that 1%. You're still only going to be 100 times faster. You can never make that code 1,000 times faster. And for certain application domains, that's the analysis we have to do first. If you start to do that analysis after the fact, you're going to be pretty disappointed in the path you took. So that's the takeaway. Make the common case fast. Have a common case which has a really large F value. That's an important takeaway. But then you're always going to be limited. No matter how good you get in terms of generating an alpha value, you're always going to be limited in terms of that 1 minus f component here. The textbook and the lecture then goes on to talk about power trends and dynamic power consumption. And I think that is an important topic, but the book doesn't cover it very well. And so I think for now we can probably just skip by that entirely, and I won't ask you any questions about power trends. This is where we have a little bit of a hole, and a 481 class would probably be the right place to cover such a topic, looking at how beyond just the performance equation, the things we do to improve performance also have a potentially negative impact on our power consumption and how we resolve those issues. That tends to be, the resolution for that tends to be a more advanced architectural subject. So I'll leave that part here untouched for this semester based on how we're doing in terms of schedule. And you're very welcome to read, and certainly very welcome to ask me any questions about it offline or not, but I'm not going to require us to become really fluent in the dynamic performance consumption, power consumption equation. If you take VLSI courses, you'll get a little bit more of that in those courses. It's also very much an architectural topic. So in terms of Lecture 5, you don't have to look into that material. You can, you're very welcome to, but it's not going to be a requirement for this class. Because I had promised for today, and at the best we'll be able to do is just to start it today, and certainly not to complete it, would be to look at FPGA design and what that means for where this class is heading, because we will be doing FPGA design mostly under the hood, but it is going to be there. And first off, I'm not sure to what extent people who are in this class, you've taken 281, remember what an FPGA is. So, okay, this is representing a change of scope here, change of topic. And we'll get as far as we can get, and then I can clean it up either Monday or at some other point. So FPGA, which we are going to start using, is a field programmable gate array. Does that sound somewhat familiar? Yes. No. That's fine. It is a special type of circuit that allows us to prototype hardware. It's not magic, and we can actually stare into the internals of one today if we have the time to do so. It allows us to prototype different hardware via synthesis down to a particular type of computing fabric that allows for multiple changes of what the hardware is doing. And it is a little bit magic. At least the first time you get it to work, it can feel like magic. But it's a very necessary step for one reason, that everything we've done so far in terms of our hardware design portion of this class has been all about behavioral simulation, which is useful. In terms of our design flow so far this semester, we've been spending a lot of our, well, I guess I should talk about the schematic entry and things like that, but no one's been actually making nice diagrams by and large. So we've been starting with our VHDL source. And then we've had this loop, a very important loop, I think, which is compiling that code and being in ModelSim and doing behavioral simulation. And I've been hinting but it's only been hints really so far. And this is a loop, definitely, right? If it doesn't compile, you're back to the source. If it compiles and doesn't work, which unfortunately happens to us sometimes, you're back to the source and you're trying to reason about what's happening. That is actually a very small portion of our hardware design tool flow. Not saying it's trivial. Obviously, you've put lots and lots of hours this semester into it. You've been learning a lot as you've been going, but it's a very small portion of it. And when we actually want to be building hardware, there's several other stages that are needed. Let's talk about the tooling for this to begin with. Well, first off, so an FPGA is a particular chip that you would purchase, and typically you wouldn't purchase the chip in isolation. It'd be part of an FPGA board. I don't know if this is what I'm going to try here is going to work, but let's give it a try and see what happens. Um, I have my phone pointing at the FPGA board next to me here, but it is a little slow. Okay, so there we go. So that is an FPGA board. That is, can everyone see that? Thumbs up if you can. Okay, thank you. That is a Nexus Video FPGA board. It's a pretty nice one. You have some experience with the DE2 boards for CPRE 281. And ultimately, yes, there's nicer ones and there's less nice ones. They're as cheap as $49 and it's expensive as $49,000 and everything in between. But they all are really similar in terms of what they're doing. That wacky looking heatsink is blocking the actual FPGA. And generally, for this type of evaluation or prototyping board, what the manufacturer for the board would be providing would just be as many peripherals as are needed. So that is going to be a problem. Hold on one second. People are going to be sending me notifications while we're doing this here. Well, anyway, you don't need to see the board anymore. That is the FPGA board. And it's going to have those peripherals that are needed to interface with the rest of the real world. So in isolation, it's just a chip that has a bunch of I/O associated with it, and you oftentimes are wanting to prototype an end-to-end solution. So things like interfacing with Ethernet was there, and USB and video and things of that nature. And then there's a whole separate class of tooling we use to develop for FPGAs that has a lot in common with ModelSim, but it's actually a superset of what is available in ModelSim. You've had a little bit of experience in Quartus. You're going to get a little bit more experience this semester in Quartus. I'm not a fan of Quartus at all, and it's also very much manufacturer dependent anyway. So the tool that I use for these Xilinx chips that we tend to use for our research projects is referred to as Vivado. And I opened up a copy of Vivado earlier in the semester, and here it is again. If you think ModelSim's annoying, I would say multiply that by about 15, and that's the annoyance of Vivado. Just the features, just the things that should work that don't. But it has a lot in common, and I do think as you've become really fluent, and I've seen a lot of you have in using ModelSim and becoming a ModelSim expert, that general skill set of how to navigate a commercial electronic design automation tool is going to potentially be very helpful for you, later in life, because they're different. They all do different things. They have a lot in common, and just how well the company pays their engineers tends to be the main distinguishing. Their software engineers is the distinguishing factor. So for Vivado, we can very quickly create a project that is targeting that board here. And I'll just walk you through it. Everyone can kind of see that screen. You don't need to know all the really tiny font here. I wouldn't normally do the create a project wizard, but it works for the purposes of what we are doing today. We're going to create just a new project, throw it in that random directory. And there's many different types of projects here, but for our purposes, what they would refer to as an RTL project would be a VHDL and Verilog project here. And the nice thing is I've already configured this tool to be aware of the board that I have sitting next to me here. So I'm just going to select that board. That's a very useful thing because that tells us things like specifically which model FPGA are we targeting, what packages is it, what speed grade it is. It knows a lot about the board now because of the engineers at Digilent provided a package to describe what's happening inside that board. And as we open up this tool, it's got a lot of stuff going on, no doubt. But it does have, a Tickle console. So that should look kind of familiar, right? That's like our transcript window and model sim, and the same philosophy kind of follows that, right? That everything you can do in the GUI has the equivalent tickle command below that you can copy paste and script, and that's the actual recommended way of doing version management with Vivado is by sharing those scripts and uploading just those scripts. We have a empty design here, so we can now say let's add a source. And to start with, let's add a design source, and let's create a file. We could do Verilog, but let's do VHDL, and let's just call it. Top is a pretty common name. It's the top level design. We'll just call it the example.vhd. And the GUI is kind of interesting. Let's see. Okay, yeah. The GUI is kind of interesting in that it does attempt to hold your hand a little bit um, with regards to auto generation of source if you want it to. So we can use this. We can just skip, I think, but we can also say, well, let's call our architecture behavioral. Remember, that's just a label. We could have called this Joe, and it would have been perfectly fine. But behavioral is fine. That's just the architecture name. It also allows us to, if we want to generate some ports here, you can just click and specify your ports. Let's create a clock and a reset. And one thing you could see on that board, and there's a lot of I/O. Definitely the easiest I/O to work with. That's going to keep reconnecting each time. The easiest I/O to work with are those LEDs and those switches near the the bottom of that screen there. So there's 8 of them, and you wouldn't know that off the top of your head, but I've worked with this board quite a bit. So we have some switches, which would not just be a single switch, but would be a bus of 7 down to 0. Likewise, that would be an input. We would also then have some LEDs, which would be an output port of 7 down to 0. And when we select that, this should then generate a design for us, which we can open up. And it should look like, maybe it's a little hard to read here. I don't think I can easily increase the font size of it, but it should look very similar to the type of code that you would have been creating, right? It's got our entity block, it's got our input port and output ports and so forth. And we can do any sort of design that we want, obviously, right? This is very straightforward thing. So we could just say, let's create a process. I don't know, that takes the values of the switches and maybe we can invert it or something like that. So if rising edge of clock, let's set the LEDs to the inverse of the switches. This code editor is awful, just like Model Sims is, but we use it if we're doing a demo of this. Begin and process. What are the odds this will actually compile? It should tell us if it's trying to or not. So it's doing various analysis runs. The other thing that's definitely necessary, because this is an FPGA-based design versus just something that you're simulating in Model Sim, is those signals that we've just created have to correspond to something physical on the device. And right now, we just have a design that has some behavioral functionality associated with it, and we can simulate it, right? So we could take this design, and I'm scared to think how long that's going to take to actually run, but we could tell it, hey, compile this code, run it in, this is in Vivado Simulator, which is very, very similar to Model Sim, and allow us to test if the actual running of it does what we would expect it to from a behavioral perspective. Looks like that caused me a technical problem here. 1 second. Yeah, we're having some stream crashing. It doesn't surprise me that Vivado does it. Can you guys? That might have restarted. Can you guys still hear me? All right. So let's leave things here for today. And I will continue this on Monday because I think this is an important walkthrough to do. Thanks for letting me know. And I don't know what the issue could be, but it's probably on my end. So Vivado and Zoom maybe are not playing nicely together. That wouldn't shock me either. But let's leave things here for today, and we'll do this properly on Monday. So I want to be able to show this to you, show what's possible with this tool set, and then we'll jump into what would be lecture 6 otherwise. Hopefully the video is not completely ruined, but if it is, you'll be fine anyway. And otherwise, good luck on the work that you have this week with Project Part A, and I will see people on Monday.